Good evening and welcome to the live sessions for the course Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but participants are yet to join. So we will wait for a few moments before we get started. Thank you. Good evening and welcome to the summary session for the course Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a member in the faculty of the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Over the past 12 weeks, we have looked at various aspects of additive manufacturing, starting from its definition, the terminology, what aspects or characteristics qualify a process as an additive process, as opposed to, say, a subtractive or a formative process. We have looked at the various stages of any additive manufacturing build cycle, starting from the pre-processing, where we uh, design our model in a CAD environment, to how we slice it, what are the characteristics, what are the various criteria for slicing, how can we optimize our slicing method for, say, either maximum build rate or for good geometric accuracy. We also studied about adaptive slicing, conformal and non-conformal slicing, and looked at various scenarios where each of them might be applicable. We looked at the various classification of additive manufacturing technologies, and we also looked at both the standardized ASTM classification as well as the classification based on the type of feedstock used, and stuck with the latter for the remainder of this course. Now, in successive weeks, we have also looked at various additive manufacturing processes, mostly by breaking them down at the subsystem level. Say, what was the powder feeding subsystem, what was the scanning system, what was the optics, and so on. What was the build environment like? And starting from the additive manufacturing of liquid materials in processes such as VAT photopolymerization and binder jetting, then on to say wire-based AM in DED and arc-based additive manufacturing methods, then powder-based AM, both blown powder and powder bed type, and this allowed us to cover the wide gamut of all AM processes that are currently known to us. In addition to existing well-known commercially established machines and processes, we also looked at some upcoming and research stage processes which also offer the promise of certain unique benefits and functionality. And thus, we have spent the past 12 weeks very productively uh, taking a holistic overview of the AM processes. Now, in this summary session, we would just like to revise and summarize whatever we have studied and maybe look at some additional aspects of AM processes, and for this session specifically related to the numerical modeling of additive manufacturing processes. And for this, I have borrowed these slides uh, from Professor Swaroop Bag, and the content of this session are also available as that supplementary material for the course on the YouTube playlist. So let us get started. Please excuse me one moment. So let us continue. Additive manufacturing, as we know, is a layer by layer manufacturing process, and typically these layers are decided at the time of slicing. So an AM process must necessarily originate from a digital CAD model. So the well-known uh, file formats are STEP, IGES, or STL. STL is being the most commonly used file format for additive manufacturing processes. However, other formats such as AMF or 3MF, which is the additive manufacturing format, is also coming up. And each of these has distinct advantages and disadvantages. While some may be very light and easy to work with, others may be more comprehensive in terms of the information that they can store, such as the material, the color, the texture of the part to be built. However, this would also result in the file size being somewhat larger as well as uh, increased complexity in the file handling. And additive manufacturing creates 3D objects, but it should not have any subtractive or formative methods involved. So subtractive methods are when we are removing material from a primitive such as a cube or a cylinder, a cubical block or a cylindrical block to arrive at the final desired geometry. Whereas in additive manufacturing, we are only depositing the material in the required regions to end up with the final desired part. However, as we already saw, there are certain additive processes which are inherently hybrid in nature. And when we say hybrid, what we really mean is that they will have both additive steps and at least one subtractive step, such as all sheet additive manufacturing processes, also commonly known as laminated object manufacturing, are inherently of a hybrid type. Apart from this, subtractive steps are also needed in the post-processing stage of most additive processes, and the reasons can be varied. So you may require a subtractive step to achieve the desired surface roughness, because as we know, typically the as finished surface roughness for most AM processes would be pretty coarse and not really suitable for any end application. Also, we may need some post-processing steps for removal of the support structure, which again would qualify as a subtractive step. Apart from this, there might be some non-subtractive post-processing steps also, such as hot isostatic pressing of powder bed fusion parts, and which are performed with the direct aim of increasing the part density and reducing porosity. So, as per the definition, the processes should not have any formative or subtractive steps, but we are well aware that there are certain processes which do qualify as additive processes while having at least one subtractive step with them. And since it is an additive method, the materials are utilized effectively, as in material wastage is kept very low. Because as I said, in our conventional process, we would start with some primitive, such as a cubical block or a cylindrical block, and then we will successively remove material from it in a way so as to arrive at the final desired geometry. All the material that we are removing is actually getting wasted, and it is very rare that this wasted material in the form of say chips can be recycled or reutilized. Whereas in additive processes, instead of removing material from an existing primitive shape, we are only deliberately adding material in 3D space in regions where they are required, and for all other regions, we do not deposit material, or in certain cases, we may deposit some support materials, which will again be removed later. Even the support materials are weaker, or we can say less dense than our build material. And so overall, the material is utilized more effectively than in a conventional process. Any additive manufacturing process will create objects according to a 3D model, and this is one of the requirements that all AM processes should originate from a 3D CAD model of an object. If it is not, then the process will not qualify as an additive manufacturing process. A computer interface is definitely required, be it for the design of the 3D CAD model, be it for the slicing, or after slicing, whether it is for the generation of the toolpath along which our machine will deposit the material, or whether it is for passing this toolpath onto the IM machine, whether it is for, say, monitoring the process while it is happening, or for actively changing the process parameters while the process is still running. All of these uh, steps will require a computer interface, and thus it is very much a digital manufacturing process. It cannot be accomplished without computers. And the surface roughness of as-built parts, while it may be adequate from some processes such as VAT photopolymerization or also some types of binder jetting, however, for most processes, you would require at least one post-processing step to achieve the desired surface roughness that is mandated for the final application. And here again, we have an example that shows the need for adaptive mesh slicing. We have this ellipsoidal object which is sliced almost uniformly, and the question that is posed to us is whether this layer thickness is optimum, whether the given layer thickness will be successful in capturing the curvatures that are involved in this geometry. And the answer, as we know, is no, because in some regions say near the equator, these layer thicknesses might be still be okay, but as we near the poles, here we need much finer layer thickness in able to so that we are able to capture the curvature of the geometry. If we work with such very thick uniform layers throughout, we will fail miserably at capturing the part geometry accurately. Now, a slide that summarizes the importance of additive manufacturing processes. So, AM by definition is the process of building three-dimensional parts by adding material in a layer by layer fashion based on a digital model. This layer by layer terminology is very important for any AM process because 3D printing, as additive manufacturing is also commonly known as, it is very similar to 2D printing, except that we just have added a Z axis to the printer so that at any time it is working exactly like a 2D printer, but then the bed or the head shifts in the Z direction by a predetermined distance and is able to deposit the next layer, which is what results in the 3D character of the printed object. Some other advantages are design flexibility, that is, you are able to design objects which were previously not feasible to manufacture with conventional processes. A common example of this would be lattice structures, which are very difficult to realize from most conventional processes. Relaxation on assembly because of the reduced part count. Again, because of the design complexities. Earlier, a complex part would have been made of, say, multiple subparts. There is a famous example of a LEAP engine, GE's LEAP engine nozzle, which earlier was made up of 31 parts, which would then be assembled together very precisely. But with additive manufacturing, it can be realized as a one part in one step. Reduced lead time and material wastage are the few benefits of additive manufacturing technology over conventional manufacturing processes. And in the modeling or analysis of any such additive process, some of the most crucial aspects are motion control, the representation of the heat source, and the representation or addition of the feedstock. As we see here, first we have a two-dimensional view where layer by layer addition is depicted. And as we see in the figure to the bottom, the material is being added progressively, and any numerical or computational representation of such a process should also ensure that this interaction is captured. That is, the material should not be, say, made available all at once. Rather, it should be added progressively to the system. Now, a classification of additive manufacturing processes based on the type of energy source is given here. For the processes which utilize a beam as the energy source, we can either have a laser beam or an electron beam. Laser beam, again, when used in conjunction with a wire feedstock, results in a process which may be generically called as wire laser additive manufacturing process, such as your laser wire DED. When used in conjunction with a powder feedstock, the powder may be available either in the form of a stationary bed, and such processes are called selective laser melting or selective laser sintering. The ASTM standard terminology is also powder bed fusion, because here the powder is already available in the form of a reservoir or bed, and the laser scans over this region of interest to melt or sinter, as the process may be, the powder over the desired regions. When the powder is not already available in the form of a stationary bed, but is delivered uh, in synchronous motion with the laser, then such a process may be called as a blown powder additive manufacturing process. One of the examples given here is LENS, which is a trademark of Optomic Technologies. I believe it stands for laser engineered net shaping. Other term used to describe similar processes may be a powder DED. Now, when the energy beam is in the form of an electron beam as opposed to a laser beam, again, depending on whether the feedstock is wire or powder, the process can be called as an electron beam additive manufacturing process, or in the case of a powder bed uh, type feedstock, the process will be called as electron beam melting. We also discussed at length why blown powder cannot be used in conjunction with an electron beam, because for operation of an electron beam, also for generation of an electron beam, we require high vacuum. The magnitude of this vacuum will be typically of the order of 10 to the power minus 9 millibar in the gun chamber, where the electrons are extracted and the beam is generated, and 10 to the power minus 5 millibar in the working chamber, where this electron beam travels through to interact with the powder bed. If we are using a blown powder setup in conjunction with this electron beam, the powder will have to be carried by a carrier gas, which is typically the same inert gas which we use to, say, shield the melt pool or to shield the optics. The introduction of this carrier gas into the working chamber will lead to loss of vacuum, and once the vacuum is lost, the electron beam will not interact effectively with the target material, because electrons are very light particles, and the way they transfer energy to the target material is via their motion, is the kinetic energy that is later transformed into heat energy and results in melting of the powder feedstock. Should an beam of electrons encounter other heavy particles such as inert gases in their path, they will simply scatter and they will not be able to reach the target surface. So we will not really be able to print anything. So when powder feedstock is used in conjunction with an electron beam, typically it is always in the form of a powder bed. We also saw comparison of a laser beam versus an electron beam, and typically we saw how laser beams can be focused to very small spot sizes, whereas there is a physical limitation on the spot size of electron beams. That is because, for a given flux of electrons, because of the repulsion between these like charged particles, they can only be brought close together to a certain extent before they start to repel, and the beam starts to diverge. Whereas in the case of lasers, which are basically photons, it is a beam composed of photons. There is no such physical limitation on the size. However, the laser beam size is decided by the technological advancements. On the other hand, rather than using a beam, if the energy source is in the form of an arc, then the processes may be similar to TIG, MIG, or plasma welding, and typically they would be, say, performed in conjunction with a wire feedstock. And all such processes are categorized as wire arc additive manufacturing. Here we also see, say, schematic diagrams of the typical laser additive manufacturing processes. On the left is a powder bed laser-based additive manufacturing setup, where we have our working chamber, we have the laser beam. You also see the inert gas getting purged, which is used to keep the region or the working chamber free from air to prevent oxidation of the powders. We see the recoater roller in this case, which after every pass spreads a uniform layer of powder over the print bed. And we see the feeding tank and the collecting tank, as well as the build platform, which lowers down in every step by a predetermined height. To the right, we see a powder feed based laser additive manufacturing setup where we have the laser beam and the optics or the focus lens. We see ports for the shield gas and the powder delivery. And we're also seeing how the powder is flowing into the path of the laser to form the molten bead. Now, in powder bed based laser additive manufacturing, a 3D CAD model is sliced into planar layers and a scan path and build files are generated. These build files are then passed on to the machine. In each pass, a thin layer of powder is spread over the substrate and high energy density laser beam scans over the bed in the XY plane to fuse the powder particles under computer control along the desired path. The build chamber is filled with purified argon or nitrogen, which provides protection against oxidation by purging oxygen from the chamber, uh, making heat conduction more effective and enhancing the cooling. An entire layer is built pass by pass, and the z-axis is then lowered to spread a fresh layer of powder by a recoater blade. During the course of our discussion, we also looked at how uh, the recoater may either have a blade-like morphology or it can be a ruler, or it may be a frog feeder, or in certain cases it may also be, say, an electromagnetic recoater. And we also checked what advantages each of these types offer. For the powder bed process itself, there are multiple parameters which must each be tuned and optimized to achieve the perfect part. When I say perfect part, I mean a part which is devoid of defects, such as cracks or porosities, and which has good mechanical properties equivalent to rod parts, and which also conforms to the design requirements in terms of the geometric tolerances and the surface finish. The SLM process is controlled by a set of parameters related to the heat source, build strategy, powder material, and other process characteristics. In terms of the heat source, we must optimize the laser power that we are working with, the beam size, whether it is a very small size beam or a large size beam. Typically, a small size beam is used for scanning the contours, whereas a large size beam is used for the infill region. An even larger size of beam may be used for preheating the powder bed, should it be needed, or for remelting the already printed layers. However, typically you will not really alter the beam size during the process. Mostly it is only done at the start of the process. And depends on whether we are using a continuous laser or say pulse laser. If it is pulsed, then the pulse duration and the pulse frequency also come into the picture. And varying these parameters will vary the final build quality, build properties, and also the geometry of the build. Next comes the build strategy parameters, which can be the scan pattern, whether it is simple unidirectional scanning, bilinear, zigzag, raster, spiral, any fractal path, or any other path depending on the requirement. Then comes the hat spacing, uh, and we also discussed how there exist some geometrical models for predicting the optimum hat spacing in order to have an almost planar layer of material. And we saw how typically it is equal to two-third the width of a single bead. So if we keep our hat spacing equal to two-third the width of a single bead, it is expected that will have an almost planar layer, the XY plane. Uh, Keeping the hatch spacing optimum is also necessary to prevent intralayer interlayer porosity, that is, in the deposition of one bead adjacent to a previously deposited bead. We must ensure that there is sufficient overlap and no pores in between. Next comes the scan speed, and as we discussed, changing the scan speed will change the energy density that the material is subjected to. So if we scan at very high speed to enhance the build rate, the localized energy density in any region may be too small to allow the powder to reach melting temperatures, and thus it may only be partially melted or just sintered or only heated. So the scan speed must be optimized. If the scan speed is kept too low, we may end up with very deep melt pool, which may not really be conducive, and also the build time will be exceedingly large. So an optimum value must be used. Then the feed material itself, in terms of the powder shape and size. The shape, as we know, typically we aim for spherical powder particles. Depending on the type of process used to generate the powder, the shape will differ. So whether it is based on just mechanical grinding or pulverization, or whether it is an atomization process, whether water atomization, gas atomization, or plasma atomization, the sphericity of the obtained particles will differ. In terms of size, while we do aim to keep powders of a predetermined, say, mean size, we do know that it is impossible to obtain powder particles of only one size. Rather, we always have a distribution. The distribution can be tightly controlled, so it can be a small distribution compared to a wider distribution, but that will drive up the costs. Also, we saw how sometimes it is indeed useful to have powder particles of multiple sizes, say a few min-sized particles, few larger than those, and a few very small sized particles, because then the overall packing density comes to out to be very high compared to, say, an array of powders of one uniform size. Powder distribution, as we discussed, should be controlled. The layer thickness, we can have a larger layer thickness in regions of simple geometrical complication and to improve the build rate. However, for thick layers, the geometrical accuracy may be lost. To capture geometrical intricacies such as curvatures, we need to have very small layer thicknesses. However, if we were to print our entire build with only a small layer thickness, the print times will be unrealistic. So we must use adaptive slicing to determine which areas can be printed with coarser layer thickness and which regions require a fine layer thickness for printing. And finally, the properties of the feedstock material itself. So how pure it is, whether there are any contaminants present, whether the powder is already oxidized, or whether it is some pre-alloyed powder which can have some additional, say, corrosion resistance or strengthening properties compared to just a base alloy. All of these factors will define the final part properties. Then there are certain process specific parameters which must also be tuned. So for the specific case of powder bed additive manufacturing, it can be the powder bed temperature, whether we are incorporating any preheat or whether it is at ambient temperature while starting the process. As we discussed, preheating is typically used to avoid the generation of tensile residual stresses. Tensile residual stresses are generally experienced when large temperature gradients exist in a powder bed setup. And to decrease this temperature gradient, we can preheat the powder bed to say some anywhere between 300 to 600 degrees. So that now when the powder is deposited with some superheat, say 1600, now the temperature difference between the deposited material and the bed is only 1000 compared to say what would have been uh, nearly 1600 before. So this can lead to reduction of tensile residual stresses. As we know, tensile residual stresses are the ones mostly responsible for delamination, cracking, and other similar defects. Also important is control of the build chamber environment. We saw that in some processes such as binder jetting. Uh, we need not really control the environment, and the chamber can be open to surrounding environment because of the low working temperatures and the general inertness of the processed material to corrosive or oxidative environments. Whereas in other processes such as electron beam melting or in powder bed fusion, the chamber environment must be carefully controlled to purge out all the oxygen to ensure that the powders are not oxidized and the parts are printed with expected quality. On the other hand, in powder feed-based laser AM processes, 3D components are built by locally fusing multiple layers of powder feed material onto a substrate. Whereas in powder bed type processes, you already had a bed of powder. The powder was being spread over the printing area in every pass, and the laser was simply scanning over it. Powder dynamics did not really play a role because the powder was already stationary at the start of the process. In this case, the powder is directly deposited only in the regions where it is needed in synchronous motion with the laser. The powder is delivered in the path of the laser via carrier gas, and it absorbs some energy from the laser beam, which may lead to a temperature rise or in certain cases even melting of the powder during its flight path. Then this fully or partially melted powder is deposited onto the bead and leads to the formation of the printing part. In the building chamber, laser beam focuses on a point on the building platform, forming a melt pool into which the powder is fed. So here the laser interacts both with the material that is being deposited and the substrate of the pre-built layer. So a part of the energy of the laser is absorbed by the powder particle in its flight, which may lead to its temperature rise or even melting. The rest of it goes into interacting with the pre-deposited layer of the substrate, where again it is expected that the laser beam will create a molten pool of material into which this heated or melted powder will be fed. After one layer is melted, laser head and powder nozzle move up, and the laser heating and injection process repeat for the next layer. However, either the laser head and powder nozzle can move up or the bed can also go down. It depends on the design of your machine. As we know, laser optics can be fragile, so it may be preferred that rather than moving laser head, we are just simply shifting the bed by the predetermined distance in the negative z direction. This process can also be used for part manipulation and repair. That is, deposition can be carried out on an existing part. We also saw an example how laser DED can be used for repairing of existing parts which may have failed in service. This can be done by scanning the broken part or the part to be repaired and generating a toolpath only for deposition in the region which requires repair. And the laser can be made to scan selectively over those regions only, deposit the material, and with a little post-processing, the part can be made as good as new. Typically, this process would be almost impossible or difficult to realize in a powder bed type setup because the repair geometry can be arbitrary. Unless it is planar, it is really difficult to realize it or repair it in a powder bed setup because in every layer, your recoater will spread a layer of powder over the existing machine, existing part. Even if you dip the entire part in the powder bed, if some region is protruding, it can collide with the recoater blade and the process can stop. The DD type process also offers other advantages, typically in the making of large parts, and that is because the powder bed-based system is limited due to inherent cost and build time, and also because of the need for environmental control. In a powder bed type setup, we need to fill the entire printing volume with powder, irrespective of the say the size of the actual part that you want to realize. Whereas in powder fed additive manufacturing processes, we can only have a quantity of powder which is commensurate with the volume of the part to be built. Of course, some of the powder will be wasted, and typically such waste can be calculated via the catchment efficiency, which is how much powder actually got deposited into building the bead as a ratio of the powder to the powder that is originally flowing from the powder nozzle. A coaxial feed of powder or wire to a laser electron beam to form a melted or sintered layer on a substrate is also how a DAD process may be described. Powder deposition is synchronized with the heat source. Here the powder is deposited in sink and no powder bed or existing layer of powder is used. Scaling up of DAD is more easy and cost effective to produce larger parts. DAD, as you know, can also be used to coat existing structures. Such a process is called cladding, laser cladding, and this finds important applications in repair of cracks or defects, in providing wear-resistant coatings to particular areas, or in protecting specific areas of an object from corrosion. On the other hand, are various wire arc additive manufacturing techniques. So they can make gas metal arc welding, where an electric arc is formed between a consumable electrode and a metal workpiece. Different modes of metal transfer, depending on the working characteristics. It can be globular, it can be short circuiting, a spray or a pulse spray, and generally associated with high melting efficiency and higher deposition rates. However, higher deposition rates also imply that the geometric tolerances are on the poorer side. Cold metal transfer is the standardized process, and this is a modified MIG welding process based on short circuiting transfer process only. This also happens at a relatively lower temperature, and that is why it is called cold metal transfer. It is not really cold in the absolute temperature sense, but it happens at a lower temperature compared to other processes. This differs from MIG welding process only by the type of mechanical droplet cutting method, and the droplet detachment mode of CMT is without the aid of electromagnetic forces compared to the conventional MIG process. So the spatter is decreased. As we remember, here the wire is melted and the molten volume of material is lowered into the existing bead or melt pool. And once they make contact and the short circuit is detected, rather than relying typically on a shooting up of the electric current, which will lead to joule heating and then lead to breaking up of the wire because of the localized heating, we mechanically pull the wire back whenever such a short circuiting is detected. This prevents the spikes in temperature and also lowers the amount of spatter. So, thank you for your patience. So I'm a little under the weather, so I'm just taking this momentary break to drink some water. That's it. Next, we look at the numerical modeling aspects of additive manufacturing. As we know, the objective of any numerical modeling or any modeling approach for that matter is to model a physical phenomenon in terms of into a mathematical description with some governing equations, some boundary condition, and maybe in some cases some initial conditions as well. It will always be an approximation, but it can come really close in describing the actual expected output of a process. However, typically it is nearly impossible to model all the physics involved in any process. So we only resort to modeling the most important physical phenomenon, which are critical to the output that we desire. So the Various physical phenomena that occur rather simultaneously in any EM process are the melting, solidification, vaporization, phase changes. So material is deposited by melting. This molten material later solidifies based on the cooling rates, based on the surrounding conditions. The solidification microstructure will differ. Also, if the temperatures reach sufficiently high, there can be vaporization, and this selective vaporization is often responsible for the change of alloy composition in the deposited part compared to the nominal alloy composition that was present in the feedstock. On the free surface, there can be surface tension dominated free surface flow, which is typically referred to as the Marangoni effect or the Marangoni convection. So in the liquid, depending on whether the surface tension gradient has a positive slope with temperature or negative slope with temperature, that is to say whether it increases with temperature or the surface tension decreases with temperature. You can either have an inwards flow or an outwards flow from the center of the melt pool. If it is an inward flow, we will have deeper melt pool, whereas if it is an outward flow, we will have shallower melt pool. This effect can also be affected by the presence of certain surface active materials such as sulfur. Next is modeling of the heat and mass transfer process. Another is modeling of the moving heat source. And finally, uh, one critical aspect is modeling of the free surface of the bead because that determines the final bead geometry. Now, any effective numerical model would be useful for assessing the impact of process parameters and for predicting the optimized conditions. Further, transport phenomena such as heat transfer and fluid dynamics, buoyancy-driven flow due to temperature and species gradient, or surface tension dominated free surface flow will strongly influence the microstructure and the mechanical properties. And the surface tension driven free surface flow determines the shape and smoothness of the clad. Other aspects are the solidification of alloys, that is, at the mushy region, and the transport phenomenon occurs over a wide range of time and length scales. The mushy region is the region between the solid and liquid fronts where you have both solid phase material and liquid phase material. The evolution of the interface between different phases or different microstructure constituents, coupled with physical fields such as temperature and concentration, and certain approaches are named here. They can be phase field approach, front tracking approach, immerse boundary method, and level set methods. And these methods typically only apply to small domains on a continuum scale from about zero point 0.1 micron to 10 mm. 10 mm indeed is very large when you're talking about these processes. Typically, they'll be in the micrometer range only. Whereas often for engineering applications, we are more interested in part scale results, where I can predict whether there is any distortion in the part, whether there is any porosity in the part. And so what we really need is actually a multi-scale modeling approach, where some insights can be gained at the micro scale, some insights at the macro scale, and these two can be linked to a suitable physical model to come up with overall predictions that can determine the part performance. Thermal analysis can be performed independently of the mechanical analysis, as change in thermal boundary conditions due to deformation is negligible. Also, the plastic strain energy during deformation is very small compared to the input energy. Also, this is typically what is implemented in most models that we come across, where they only do a thermal analysis. Often it is only a conduction only analysis, that is in the solid state only. Of course, there are various techniques to account for phase change from solid to liquid, such as the apparent heat capacity method. But it is very common to just leave out the convective effects and concentrate on the heat conduction only. There are also certain reports showing or comparing the merits of a conduction plus convection model as opposed to a conduction only model. And often it has been found that while the computational cost go up exponentially, The improvements in terms of predictions are only minimal. So often researchers stick only with connection only model, but if you're concentrating on phenomena that require study of the convective processes, we should definitely aim to model those as well. It's just that they will be more complicated and also more involved in terms of computing time and effort. In weakly coupled analysis, thermal history is obtained in thermal analysis and used as input into the quasi-static stress analysis. So even if we are interested in residual stresses, what we can do is a weakly coupled thermomechanical analysis where the temperature field is calculated every time step. And this temperature field is fed as an input to the mechanical analysis module, which can then predict, divide this load into several smaller steps of loads and calculate the stress at each load step. Again, a very simple analysis can just use constant material properties, whereas a more realistic or a high fidelity model will actually incorporate temperature dependent properties. Because we know that almost all the critical material properties, starting from the density to the specific heat capacity to thermal conductivity, all are dependent on temperature and can vary over a wide range based on the temperature ranges we are working in. So a high fidelity model will always have temperature dependent properties compared to constant properties. However, for a very basic model or for an initial flavor of modeling, we can work with constant properties as well, as it will just make the computations easier and will give us some idea of what the overall process is like. Now, for the modeling of AM processes themselves, several numerical techniques have been used, including the finite differences method, finite element method, and finite volume method. And these are also the methods which are implemented in almost all the well-known CAE packages, be it ANSYS, Abacus, or any other. Additive components are typically associated with distortions and residual stresses. Also, learning or lessons from the modeling of conventional processes can be built upon, such as the wire arc additive manufacturing process in general has been found to be very similar to multi-pass welding. And so, if there is a pre-existing model of a multi-pass welding process, it can be developed further with suitable modifications to accurately represent the wire arc additive manufacturing process. And in general, most AM processes are usually simulated by means of a coupled thermomechanical finite element model. The heat transfer from the arc to the molten pool is simulated using a heat source model, which prescribes a heat generation per unit volume in the molten pool region. This heat source, it's most accurate to take it as a volumetric heat source model. So the distribution of energy would be over 3D space, and the heat source will have units of watt per meter cube. But it is not uncommon to have simpler models such as a surface heat source model, where the entire laser energy or arc energy is only distributed over the surface, and the heat source has units of watt per meter square. Or even in preliminary analysis or for some very back of the envelope type calculations, even use line or point type models such as Rosenthal's point source or line source. The material deposition in turn is taken into account by means of specific element activation algorithms. So we already know that in each layer of an AM process, the material is added uh, in a time-bound fashion. So with the movement of the laser head, the material can be deposited in a blown powder-like process or even in the powder bed process while the material is already there. It gets melted and gets fused to the growing part only when the laser scans over it. Thus, effectively, the materials may have to be activated when they are interacting with the laser source. We can already design the geometry beforehand, but the elements can be assigned some quiet or inactive value so that they do not affect the remainder of the domain. And it is only when they come in interaction with the heat source they get activated and acquire the actual computational properties. So let us just take a short break here. and we will continue after the break. Welcome back, and let us continue our session. So, we were talking about the various modeling approaches for the computational representation of any additive manufacturing process. Now, the multi-chip solidification of the material can also depend on the path taken by the moving heat source. Typically, as a first step, models only mimic a linear or bilinear deposition pattern, and we try to validate the models for such simple experiments, and only then do we try to say simulate or model more complicated toolpaths such as spiral or fractal, and a high fidelity numerical model or a complex numerical model can have certain characteristics, some of which are listed here. So they can be used for the prediction of temperature distribution. They can be used to predict the shape and size of the molten zone and the heat affected zone. It can be used to calculate the cooling rates and the solidification time. Can also be used to calculate the mass addition to the solution domain if you are trying to model the free surface geometry. Any incorporation of fluid flow of the molten materials will enhance all the calculations based on temperature distribution. Also, there can be certain material specific effects which may need to be taken into account, such as whether the presence of any surface active elements within the material is affecting the shape, size, and morphology of the melt pool. Finally, we may also be interested in predicting the residual stresses and distortion of the finished parts. Now, at their very core, any additive manufacturing process, the modeling of any additive manufacturing process will require the solution of the transient heat conduction equation, and this energy balance is represented by the equation rho Cp dou T equals minus, that is the negative gradient of Q over x and t plus Q dot x and t, Q dot being the internal heat generation rate, rho is the material density, Cp is the specific heat, capital T represents the temperature, small t represents time, x is the x is the spatial coordinate. So the current equation is a one-dimensional representation. Capital Q dot is the internal heat generation rate. Often it is here that we fit our source term. Q is the heat flux given as, I apologize. Q is the heat flux defined as minus K nabla T, and K is the temperature dependent thermal conductivity. Also important are the various boundary conditions that are imposed on the boundaries of the domain. Typically, these boundary conditions will account for the various losses, such as the convective loss or the radiative loss. In cases where we are applying the heat source itself as just a surface flux rather than as a volumetric heat source, even this heat source can be applied only as a boundary condition on the top surface. Typically, an abstract heat source model is used to represent physics of heat generation and all the surfaces of the substrate, and the evolving surface of the part being built are to be considered for convection and radiation boundary conditions. On the bottom surface, that is on the bottom of the substrate, we typically assign either, there can be various ways to model it, so we can assign an enhanced heat transfer coefficient, or we can set it to a fixed temperature if that is how our machine is designed. So typically in some machines, what will happen is this substrate plate would be tightened onto a machine build plate, which is the temperature of which is regulated, and it is maintained at some, the maximum temperature is always maintained say at 60 degrees. So in such cases we may also model it to just be at a temperature of say 60 degrees or so, or more generally we can just assign an enhanced heat transfer coefficient. The prescribed heat flux boundary condition combines convection and radiation into one single term. Typically this first term that we see here is the convective heat transfer. So this is, and the second term is accounting for the radiation or the radiative heat transfer. The value of heat transfer is generally assumed to be constant over the entire surface, and higher values are taken to simulate forced convection conditions. So typically for one entire surface, you will typically assume only one constant heat transfer coefficient. Of course, there are forced convection conditions, such as due to the flow of argon gas, and to account for those, we may have to use an enhanced or an amplified heat transfer coefficient, which will normally be higher than the one we are using for the natural convective conditions. In AM simulation, the heat source model is typically chosen as a Goldach's double ellipsoidal heat source model. This was originally developed for arc welding type processes, but later was also used for laser welding, electron beam welding, and now also for AM processes. It has certain parameters which can be tuned to best represent the exact scenario. Again, another requirement is that we need to account for the realistic heat flow distribution in the filler material, which is something the Goldach's double ellipsoidal heat source model is good at. There may be certain aspects that need to be taken into account, such as the power distribution need not be uniform. It can be different for the filler or the feedstock material and different for the base material. A part of the total power is delivered to the base material by a Goldach's model. The remaining one can be distributed over the filler material with a uniform distribution or a constant pattern. This would also allow us to capture the steep temperature gradients inside the molten pool and would ensure that the correct amount of heat to the filler material elements is provided. Now, in principle, an internal heat generation is applied to the filler finite elements whose center lies inside a brick-shaped control volume. And heat generation per unit volume is defined as the ratio between the wire melting power and the volume of elements currently heated by the power source. As we were discussing, we may require to say specifically activate or deactivate elements to simulate the material deposition, and two approaches exist. One being the inactive element method and the other being the quiet element method. The quiet element method has been discussed here, and in this case, the filler metal elements are present throughout the simulation. We are already describing the final build geometry. However, initially, quiet values are assigned to their property, or some very low values or low stiffness is assigned so that they cannot affect the or they do not have a significant impact on the transient properties of the activated material. Thus, their influence on the component behavior is minimized initially. Then the material properties are progressively switched from quiet to active values according to our deposition process. And this can be decided by an activation function, which may be triggered by temperature, or there may be some other activation function as well, say one which is determined by the movement of the laser source. And when it is decided by temperature, the material property values are computed according to the equation phi of t is equal to gamma t phi of t plus 1 minus gamma t phi q, where phi or phi q of t are the material temperature dependent material properties and gamma of t is the activation function. Now, the total amount of heat absorbed in any wire arc additive manufacturing process will be the sum of energy delivered by the arc and the energy available due to the transport of molten droplet. The convection heat transfer in the manifold exists and should be considered for accurate thermal prediction. Typically, a conduction only model will over predict the temperature distribution, and so convective heat transfer should also be taken into account. However, convective heat transfer models are computationally far more expensive than the conduction models, and to offset this, Generally, very high thermal conductivities are assigned in the melting temperature range to compensate for the increased heat transfer in melt pool due to Marangoni forces. So these are just some, say, workarounds or some approximate methods which enable us to capture the realistic physical phenomena without really increasing the computational complexity or cost. So in a conduction heat transfer model, at every step we are solving the three-dimensional conduction equation, being dou dou x k dou t dou x plus dou dou y k dou t dou y plus dou dou z k dou t dou z plus q dot is equal to rho cp dou t dou t. The boundary conditions will account for the convective and radiative losses. Typically, this is listed as kn dou t dou n minus qs plus h t minus t ambient plus uh, sigma epsilon t power 4 minus t ambient power 4 is 0. If we are only modeling half of the domain, and typically this is done to reduce the computational time, if we know that symmetry plane exists anywhere in our domain, we can only choose to model half of it. And in such a case, across that symmetry plane, all fluxes will be zero. So typically this is represented as the temperature flux dou T dou y equal to zero across the symmetric plane. The heat source can be represented as shown here. So Qs is equal to P eta Gaussian d by pi R effective square times exponential minus dx square by R effective square minus dy square by R effective square. So this appears to be some form of Gaussian heat source where the temperature, the energy intensity rather than being modeled as uniformly distributed is modeled as being distributed in according to a Gaussian function. Again, just to account for the convective and radiative losses in one term, because as you see, the radiative losses are commensurate with the fourth power of the temperatures. And for discretization of these equations by simple techniques such as a finite difference or central difference, the number of terms may become very large. It increases the computational complexity. What we can do is club them up together into one effective heat transfer term, and the effective coefficient of heat transfer has empirically been derived for one case as h equals 2.4 into 10 power minus 3 into epsilon, which is the emissivity, into temperature power 1.61. So these are just some incremental improvements that help simplify the solution of the problem without compromising the accuracy of predicted results. Now, when you're talking about transient problems, we know that the field variables will also change with time in addition to varying with spatial coordinates. So while our mesh helps us to discretize them in 3D space, they also have to be discretized in terms of time steps. And typically, the so-called alpha method for time discretization is used. It is a one-step method, and a typical formulation has been shown here. So in the most general sense, h times ti2 minus ti1 by del t plus alpha h times ti2 plus 1 minus alpha h ti1 equals alpha f square plus 1 minus alpha f1. Here the superscripts 1 and 2 refer to the two discrete time steps. So 2 can be the current step, 1 can be the previous time step. And based on the parameter of the value alpha, which will typically lie between 0 and 1, both included, the method takes on various names. If alpha is equal to 0, it is known as the explicit Euler scheme or just the forward difference. If alpha is equal to 1, it's known as the implicit Euler scheme or the backward difference scheme. If alpha is half, it takes on the form of the Crank-Nicolson scheme. Or if alpha is two-thirds, it becomes the Galerkin method. Now the load F is independent of the state of time and is basically an explicit term. And the pseudo steady state with constant welding velocity in the frame of moving coordinate system can be modeled as chi equals xi equals y minus v welding times t. This is also what has been implemented in the Rosenthal solution. Now, some important aspects of the representation of the heat source include the nature or type of heat source, whether it is arc, laser, or electron beam. The distribution of energy, whether it is a point source, whether it is a line source, a surface source, or a volume distributed source, typically called just a distributed source. The type of distribution can be over a surface or it can be over a volume. If it is a surface distribution source, typically we take a Gaussian distribution. If it is a volumetric source, some typical ones are Gaussian-like or cylindrical Gaussian cylindrical sources or Goldak double ellipsoidal sources. And the linear movement can be non-symmetric either in geometry or distribution or both. However, a more faithful model would be a phenomenological model incorporating transport. So now we are not just solving for the heat transfer, we are also solving for the species transfer. And in this case, the other equations will also come into the picture, those being equations concerning the conservation of mass, momentum, and energy. For mass, it's just dou ui dou xi equals 0. The momentum equation is rho dou ui dou t plus uj dou ui dou xj equals fi plus dou xj minus p delta ij being the canonical delta plus mu effective dou ui dou xj plus dou uj dou xi. The energy equation is also modified. Now it has some additional terms. So rho c whole dou t plus uj dou t dou xj equals dou xi k effective times dou t dou xi plus q dot. The boundary conditions will also be modified. So they are different for the top surface. The For the sides, it can be k effective dou t dou n minus qs plus h t minus t naught plus sigma epsilon t4 minus t naught power 4 equal to 0. At the solid liquid interface, we must impose a no slip boundary condition. And for such transport based models, it has sometimes been recommended that rather than modeling the source as a volumetric heat source, to reduce the computational complexity and time, it should be incorporated as a boundary condition in the form of a surface flux or surface distribution of energy. In this case as well, if there is any plane of symmetry, there will be zero flux across that symmetric surface, whether it be of species or temperature. Now, say we have created a model of an additive manufacturing process, but how can we be sure that whatever results we are getting are accurate and indeed are a faithful representation of the physical process? So the model has to be validated, and typically this validation is performed against experimental results as it is the most direct form of observation. Some such methods are shown here. In one case, the model has been validated against the thermal cycle. So you fix a thermocouple at one position on the substrate, then you deposit a few beads, and you obtain the thermal cycle. You simulate or mimic the same process in your modeling framework and generate these thermal cycles, and then you check how well your predicted thermal cycle uh, agrees with the experimentally obtained cycle. Another is also validated in terms of stresses. So you obtain the uh, experimental and simulated stress cycles and check for agreement. Often we might need to tune our model to best fit the experimental results. And once you have validated your model, you can be safely assured that whatever predictions you are making are accurate within certain error bounds. Now, another important aspect of the modeling of AM processes is the modeling of the free surfaces. So, interface tracking and interface capturing techniques are widely used in problems with moving boundaries and interfaces. This category of problems include fluid particle, fluid object, fluid structure interactions, free surface and two fluid flows, and flows with moving mechanical components. Such problems offer multiple computational challenges. An interface tracking technique requires meshes that track the interface and are updated as the flow evolves. This tracks the position of the mesh nodes in a Lagrangian fashion, that is, we travel along with the evolving interface. Imposition of boundary conditions at the interface is very easy, as the nodes lie on the boundary itself. In the interface capturing technique for two fluid flows, the computations are based on fixed spatial domains, whereas interface function marking the location of the interface is computed to capture the interface. So our grid is already fixed. The grid is pre-decided by us, and based on the motion of the interface, we are activating the grid, and there can be some activation function which can determine whether the evolving interface is within the grid or not. If we have a fine enough grid, we can actually come up with a reasonable estimate of the curved surface. This is based on the Eulerian description, that is, we are fixed in space and we are just watching the interface evolve past us. We are not really moving with it, and defines the interface implicitly on the fixed mesh. In a Lagrangian formulation, you will typically need to remesh uh, your system in each step because the boundary itself is shifting. You are shifting with the evolving interface, and your nodes must be placed on the evolving interface. Whereas in the second case, in interface capturing, such frequent remeshing is not really required. Some of the well-studied interface tracking methods are reported here. Among them are the particle methods, volume of fluid methods, level set method, and phase field method. Another method which may find application in the modeling of additive manufacturing processes is the extended finite element method, or the XFEM. And this is a numerical technique that derives from the generalized finite element method and the partition of unity method. It's a very powerful tool for discontinuous problems in mechanics such as crack growth, complex fluids, interface, and so on. It is independent of the internal geometry and physical interfaces, such that meshing and remeshing difficulties in discontinuous problems can be overcome. So the remeshing difficulties that we just discussed for the Lagrangian approach can be overcome. Uh, um, this process is such developed so as those difficulties can be overcome in its implementation. The discontinuous field is entirely independent of mesh. Enriched elements with additional degrees of freedom at crack surface and crack tips are made available, and this can be useful for simulating cracks, heterogeneous materials with voids, and inclusions. An example of such enriched nodes is shown here. So here we see at the bottom a crack growing, and we see that all the elements through which the crack has traveled, we have added extra weights or extra integration points for the nodes of those cells. Similarly, for the example above, where there might be a porosity or an inclusion, we see that wherever the boundary of the inclusion is lying, all those cells have enriched nodes where we have added additional integration points. Typically, the polynomial integrants would use a Gauss-Quadrature method of integration. An ordinary Gauss rule does not really accurately calculate the integration of enrichment functions in elements, and we subdivide the enrichment elements and increase the integration points at their nodes. Here we are also seeing certain examples of a simulation of the wire arc additive manufacturing process, and here we can see the various temperature contours. So this may be at some intermediate time step, and we are seeing how the temperature distribution is really symmetric about this symmetric axis. And so realistically, we can only simulate half of the solution domain and our results will be valid. Also, certain nodes have been chosen at these various positions defined by G1, G2, G3, and G4. And how we see that at each node, how the temperature profile will be significantly different from the other, such as at G1, it is a decreasing temperature profile. Uh, all these spikes are actually corresponding to the various passes, so we can see that there are four passes. G2, we see that for the first pass, the temperature was the lowest, whereas for the second and third, they peak before coming down again for the fourth pass. At G3, we see that the second pass seems to have the most effect, whereas for G4, the temperature diminishes rather quickly compared to the other cases. Now, in modeling of an AM process, certain other aspects must also be kept in consideration, such as that the non-uniform expansion and contraction of the material during the thermal cycle may result in residual stresses and distortions. The control of residual stresses and distortions thus becomes highly important. The most widely used technique utilizes sequentially coupled transient finite element methods, a moving heat source. The element birth and death technique is sometimes used for simulating the addition of material, and the transient aspect and the highly nonlinear material behavior can result in long computational times. In terms of the governing equations, the governing mechanical stress equilibrium equation is simply written as the gradient of stress is zero. The constitutive equation for stress strain is given as sigma is equal to stiffness matrix D times the strain epsilon E. Total strain epsilon, uh, when formulated using a small deformation theory, will actually have multiple components, those being the elastic strain, plastic strain, thermal strain, and the transformation strain. D, as we know, will be the material stiffness tensor. In one dimension, this is just the Young's modulus, but when you're talking about three dimensions, this will take on the form of a tensor. Regarding the transformation strains, solid state phase transformation alters the residual stresses due to thermal processing and hence should be considered in mechanical analysis of those alloys in which they are significant. An example is shown here, specifically for the volume change due to martensitic transformation, whereas we see that for austenitic transformation, the volume change, associated volume change is really low. Now, how to analyze for the stress and strain in additive manufacturing? The temperature history that is obtained from the thermal analysis is used as an input for the structural analysis as a thermal loading term. This thermal load, rather than being applied all at once, is divided into several load steps. And the reason for this is that if we apply all the thermal load at once, the elements may exceed the elastic limit and go into the plastic region. So we subdivide these thermal loads. However, if it is small enough, we may also directly apply it in one single step. Then the stiffness matrix with boundary conditions is formed and the displacement field is calculated. Typically, this is formulated in the form of K tilde equals F. F is the force or the load, K is the stiffness matrix, and delta is the displacement. Then we estimate the nodal displacements and convert it into stress and strain with the relationship epsilon is B times delta, where B is the strain displacement matrix. The stress matrix then can be calculated as sigma equals D times epsilon or D elastoplastic type epsilon, where D is simply the elastic or the elasticity of the elastic matrix. This can then be used to determine the effective stress and compare it with yield stress in each load step to decide the elastic or plastic yielding has occurred or not. The load steps is applied in incremental mode. When all the load steps have been completed, we determine the total plastic strain, stress, etc. And according to the Prandtl-Royce flow rule, the incremental plastic strain is proportional to the corresponding deviatory stresses. And how it is typically implemented is shown here. So we can have the incremental total strain d epsilon as the sum of certain components being the elastic strain d epsilon e, plastic strain d epsilon p, and the thermal strain d epsilon th. There can also be the phase transformation term here. Then the incremental strain is calculated as d sigma equals capital D E minus d times dou f dou sigma transpose d by d times 1 by 3g plus et d epsilon minus d times alpha tn minus 1 minus tn, where de is the elastic matrix, et is the local slope of the stress versus plastic strain, dou f dou sigma is the deviatoric stress component. Typically, these will be implemented under the purview of von Mises yield criterion and the Prandtl-Royce flow rule. And this will reduce the final matrix equation to KdL minus dLTH is equal to dB, where K is the stiffness matrix, dL is the incremental nodal displacement vector, TLTH is the incremental equivalent nodal forces due to thermal stresses, and dB is the incremental external forces. If there is no external loading, this can also be put to zero. Now, concerning the solution strategy of stress analysis model, for fully coupled thermomechanical analysis, the stress analysis depends on temperature distribution, and in turn, the temperature distribution again depends on the stress state. So this is a two-way coupled model or a strong coupling. The thermal and mechanical analysis is performed simultaneously. However, in weakly coupled or sequentially coupled analysis, the temperature field is predetermined or pre-calculated and stored as a function of time. The temperature analysis does not change the stress analysis result. So here we see some more examples of modeling. Here we also see how the mesh size can be adaptively chosen near the regions of interest and away from the regions of interest. We see that where the material deposition will take place or where the material will interact with the moving heat source, a fine mesh has been taken. Whereas in other, the remaining domain, typically of the substrate which is far away from the moving heat source, a coarse mesh is chosen. Also, when we are simulating these thermomechanical effects, we have to restrict the degrees of freedom at certain points, which may actually correspond to the clamped nodes, where the build plate is actually clamped on our additive manufacturing process. Then we can see the residual stress depth measurement as shown here on the right. Along any chosen axis, such as the z direction chosen here, we can also plot the variation in the residual stresses. The direction of residual stress is also shown here in this simulation, and we see how with the addition of multiple layers it may change. So in figure A, we have only one layer of material. Figure B, two layers, three layers in CF, and the four layers in figure D. And we see how the residual stresses are also evolving with time. Here we also see a multi-layer deposition, simulation of a multi-layer deposition using a wire arc source. And as we were discussing, for modeling of a blown powder TED-like process, the powder will, during its flight, interact with the laser beam and will keep absorbing energy. This energy may be sufficient to melt it in some cases, or in other cases, it may just be sufficient to heat it to a certain temperature without melting it. This time of flight can be calculated, and then by assuming the absorption of energy by the particle, we can come up with a time by which it will melt. So we have two particles, one and two here. One is a particle which is interacting with the laser beam for a smaller amount of time, whereas particle 2 is interacting for a longer period of time. That is how we see it on the plot on the right, that the particle one does not really reach melting point, it gets heated, but then lands into the molten pool at the end of its flight, whereas particle 2 interacts with the laser for a longer period of time, reaches the melting point, and then reaches the melt pool in a molten state. So when the particle is exactly interacting with the laser, it may not melt immediately. It needs some finite time to reach the melting point. By that time, the particles will already reach the substrate material of the molten pool, and the particle velocities may be of the order of 5 meter per second. For modeling such processes, we need to account for the catchment efficiency, we need to account for the particle dynamics, see how they are interacting with the incident laser beam. And based on these considerations, we can see how uh, the deposition profile over any chosen plane will be different, as seen in the three cases here. So to summarize, we talked about some aspects of the heat transfer and solidification behavior. We spoke of stress analysis, including volumetric dilation, and the material flow analysis. The whole in laser additive manufacturing process is when the incident power may be too high or the moving velocities may be too low to result in very deep uh, melt pool. Often because of the vaporization of material and because of multiple internal destruction, this can lead to the formation of porosities. We also spoke about free surface profiles. Some other aspects which can be incorporated is the flow behavior of shielding gas in a direct metal deposition technology or similar process. We also understood how the finite element method is an efficient technique for the modeling of additive manufacturing processes and how that microstructural modeling is truly a multi-scale modeling problem and cannot be adequately represented only at the continuum scale. So that brings us to the end of this live session and also to the end for the course for this semester. It was really a privilege to assist in the dissemination of this course and to present my interpretation, um, my ideas regarding the course material uh, in front of such a varied audience. So during the course of these live sessions, we interacted with the college teachers, we interacted with college students, some industry professionals as well, all of whom had varied backgrounds and varied level of competence in this field. And we really had an enriching experience. As I have said before, this course is perhaps the most comprehensive uh, in terms of content coverage, while also diving deep enough uh, for a level of an advanced course taught in any IITs. So this is it for this semester. So it has been my pleasure to be a TA for this course over the course of the past 13 weeks. Once again, uh, I am Sourav Goswami. I'm a PhD candidate in the Department of Mechanical Engineering at IIT Bombay, and I thank you for tuning into this course this week and all the weeks before this. I hope to meet you again in some other course or perhaps a rerun of this course again. So thank you very much.